Okay, so our idea is for, as each set of wheels rolls over the speed bump, it gets pressed down, and magnets attached to the underside, we have 5, you can't see it because it's a cross section, they pass through a coil of wire which generates an electric current, and that the charge gets stored in a battery, and then at night a switch can be turned on manually or by a daylight sensor and power the street light.
Right, so for each of our kind of coils, we're going to have 50 individual wires, so the N will be 50. We're going to use a magnet with field strength of 0.1 Teslas, and we decided to use 12 AUG, 12 gauge wire, so we'll have length of 2.053 millimeters, and we're going to use the cylinder radius of 0.5 meter. So working out area will be 0.5 squared times pi times 50 times 0.002053, keeping it all in meters. It'll give us 0.0257 pi meters squared. And we're going to assume the delta T, the amount of time it goes in and out, will be 0.1 seconds. Using the magnetic formula, EMF is NBA over delta T. We can work out EMF per each time it goes in and out, will be 4.013 volts. Now, if we turn that into power, we have to use EMF squared over R. The resistance for 12 gauge wire is 5,211 ohms. So if we square that and divide it by 500, if we square that and divide that by 5211, we shall get 3.118 times 10 to the minus 3 watts. We times it by 2 because cars have 2 wheels, or 2 sets of wheels, to get that is the amount of watts generated per car. We times it by 5 because, as we said earlier with the design, we're going to have 5 magnets per speed bump, and that will give us 0.0312 watts. Now, energy is power over delta T, so if we divide that by 0.1, that will be 0.312 joules generated per car.
Working out the traffic flow in the 24 hours, we're assuming that between 8 AM and 8 PM, we get a car every 2 seconds, and then between 8 PM and 8 AM, we've got a car every minute or 60 seconds. This gives us an average of 15.5 cars a minute. Using the fact that we've got 43,200 seconds in 12 hours, we can work out the total number of cars in the 24-hour period. We get this to be 22,320. Using a 35-watt streetlight, we can work out the number of joules required to power this in 12 hours, because it won't be on in the day. We get this to be 1.5 million, roughly. To work out the number of cars required, we do this divided by the number of joules divided by 1 car, which was 0.312. We get that the number of cars required was 4.846 times 10 to the 6. This is the number of cars required in the 24 hours. To get it down to cars per minute, we divide by 24 times 60 to get 3,365 cars per minute. In putting this into a Poisson formula, we can work out the probability of this occurring. Because putting the variables in, we get that the probability of this tends to 0, as 3,365 factorial is so large that none of these values will matter.
Okay. Right, so I looked into the feasibility of this, and basically, to start off, I assumed the average number of cars was, as before, 22,320 cars per day, and the average amount of joules per car generated was 0.312 joules. And so multiplying these together, I got a figure of 6,963.84 joules. And now the wattage of the lamp we're assuming is 35 watts. So dividing this, we roughly get an average amount of power to power the lamp at 199 seconds, which is 3 minutes and 19 seconds to power 1 light. So it's not really that feasible.
Okay, so for improvements, if we firstly used a spring on the pole under the hump, then this would have created a simple harmonic motion, which means more current would have been induced, therefore means more movement, which means more electricity. And then for the second improvement, we could have used a more powerful magnet. So in our model, we used 0.1 Tesla magnet, and instead we could have used maybe a 0.5 Tesla magnet, which would have created more electricity. And for the last one, we should have taken, as an improvement, costings could have been taken into account, so whether to see if it's cost effective or not.